would like to say welcome and extend our thanks to our invited speaker, Associate Professor Dr. Akeem Oladipo. Please allow me to introduce our speaker, Associate Professor Dr. Akeem Oladipo, the faculty member of Chemistry Department of Faculty of Arts and Sciences. Akeem Oladipo is an Associate Professor in the Chemistry Department at Esenyurt University. He was the Vice Dean of the Faculty of Engineering Science at Cyprus Science University from 2016 to 2018. And he and his team were awarded the Green Brain of the Year Award in 2017. He received his PhD and master's degrees from Eastern Mediterranean University's Chemistry Department. His research focuses on innovative material synthesis for water purification, energy storage, and conversion, as well as nanophotonic and biomedical applications. His research is also involved in material discovery and characterizations using computational chemistry, machine learning, and artificial intelligence systems. Oladipo is a member of the International Association of Water Resources, the Royal Society of Chemistry, and several other organizations, and has served on numerous conference and workshop program committees. He is currently the editor of Journal of Water Process Engineering, Bilstein Journal of Nanotechnology, Process Safety and Environmental Protection Journal, and a member of the editorial boards of Environmental Technology Journal. He was named one of the Stanford University's top 2% of worldwide scientists in 2020 and 2021, as well as receiving numerous other national and international academic honors. Today, he will give a seminar on X-ray powder diffraction characterization technique, application, and practical data analysis. Now, we look forward to welcome Associate Professor Dr. Akeem Oladipo to give his speech.
Thank you, everyone. As Sema has introduced, my name is Akeem. I believe a lot of the people already know me. I work in the Department of Chemistry, and today I'm going to talk about material characterization. One of those techniques that we commonly use to characterize material is XRD. So, this XRD can give a lot of information when you prepare materials, irrespective of the field which you are. If you are in chemistry, physics, biology, including mechanical engineering, material science, you will need to check your material. So when you know your material, you can know which application you can use it for. You can also know how to improve these kind of materials. So today, I'm going to briefly go into the basics of XRD, and I will look at some of the applications, what we can use it for. Then I will be looking at a simple explanation on how XRD actually works. Then we'll look at some of the safety in XRD. The major component of this workshop will be how to analyze and process the data which we get from XRD. So, let's look at some of those things that I will basically talk about. The first thing is, although Sema has introduced me, I would like to introduce myself again. So, I completed my master's, PhD, and postdoc in this Department of Chemistry. So, it's like I'm a product of chemistry. And over the years that I've been working after I completed my studies, my research focused on preparing different materials for different applications. During my master's, My master's was co-supervised by Professor Evan and Professor Gazi. I realized one thing in my master's study was spend a lot of time in the lab to prepare the materials, do a lot of applications, and then I send the paper for publication. My expectation is, since I spend days, months in the lab, when I send the papers, it's going to be published immediately. Unfortunately, I got 10 rejections. 10 different rejections, so I was wondering why. So I keep asking questions, why? But the why is, when I looked at the paper, and I look at the comments from the reviewers, 7 out of the 10 reviewers, they mentioned the same thing. What? They said, you have prepared all this, but we don't even know your material. Because during my master's, I only characterized my material with the FTR we have. So we have just FTR in the department, and I characterized with just this one. So they said, this is not enough. You said your material can do this, can do that. Unfortunately, there's no way we can understand that this can actually happen. So I realized that if you're going to prepare any material for any application, one of the most valuable things is to probe the function, the properties of your materials, which is characterization. But what is another problem? Even if I send my material to other institute or any place that has the equipment, do I know how to interpret my data? That is the problem. Sending the material out, getting the results, I need to explain the results. So what did I do? I started looking for information online. In fact, I had to contact some of the journal's authors, and I asked, I've seen your papers, you've done this, you've done this. What do you do? This is my data. And he said, one thing you have to do, I see that you have the results, but you don't even know how to interpret these things. Maybe you should join an association that is full of chemists. Just write your information, then they can help you. So what did I do? I decided to join some associations that are valuable. So I joined the American Chemical Society. I joined the Royal Society as well. So as a member of this, during the time I joined as a student. So I just put my question to them. I have this, what can I do with this? What can I do with that? Then I got valuable information. I realized that during this time, joining an association that is related to your department, valuable ones, will be very helpful for you. Then I move on from student membership to an associate membership level for each of these associations. To do that, you need to write exams, which I've written, and I'm certified with these associations. And then I joined several other associations that are related to my fields. Over the years, I've received several awards, and other thing is I have also attended training sections. When I understand how to characterize my material, I feel it's not enough for me. I have to see how the machine works. So one of those things I did was to attend training in Serbia. There's an institute in Serbia. There, I attended it. I saw it during the summer period. And they said if you can spend 1 month, then just pick 10 different characterization and you pay this much. It's not cheap, it's almost 3,000 euros anyway. So I decided to pay because I believe in knowledge, and I attend it. So the institute have equipment. We were trained how to characterize, how to do all those things. And as a member of Royal Society, I got an award, actually a grant. I traveled to Liverpool University, and I also get training in those things. This is just one of my membership certificates. So let's get to the business of today. The business of today is characterization. And why do we need to characterize our material? As I've mentioned earlier, it is very important to probe what the material is. If we check the functions of the material, we can easily see if we can improve on this material or if this material can be useful for anything. If you don't characterize the material, it is very impossible. So if someone tells you that this material is magnetic, really, you can put it very close to something, it's magnetized, but how much magnetism does it have? If this material is optical, but how can we probe it? So it is very important to do characterization. Now, we have a lot of characterization techniques. I'm just going to mention a few of them. One of those common ones is this microscopy. So it's a characterization method which you use in different aspects of science. This particular one focuses on just the surface and subsurface of a material. So a material will be interacted with maybe electrons, ions, or protons, just to see what happened to the surface. And we have a lot of different characterization techniques under this microscopy. Then, the common one that almost everybody knows is spectroscopy. In spectroscopy, we can actually deal with the composition, the amount of material in any samples. And we have different types of spectroscopy. We have those ones that are related with lights. Everything about spectroscopy is related with radiation. One of those electromagnetic radiations is being used to bombard the material. And what each one of them do is different. If you look up there, we have the UV visible, which is the common one we have in the lab. And then if you look at the one I'm going to talk about today, which is the X-ray. So the question is, what is the difference between the UV and X-ray? They are all spectroscopy. So the difference is majorly two things. The type of radiation that is used. So we see the UV, it uses radiation which could be under the UV lights or the visible. And X-ray use X-ray. But the thing is this, which part of the material does this radiation attack? When we have UV interact with the bonding electrons in materials. We have what we call the bonding electrons, non-bonding electrons, and we also have the inner electron, the core electrons. So the UV is able to interact with the bonding electrons. But then the XRD, it interacts with the core electron, the inner electron, not the bonding, the inner electrons of the material. We also have various ones. We have like NMR. NMR, it will interact with the nuclei of the material. Now, which kind of light does NMR use? NMR is not here, but he uses the light of a small energy, radio waves, to interact with the material. So we've got a lot of them. But my focus today is going to be on XRD, and I will jump quickly into that. So, this XRD, what it is is a technique that is actually used to probe the crystal information of any materials. This method is actually non-destructive, and it can actually be used for almost any type of materials that contains atoms, molecules. Now, this material could be some sort of amorphous material. It is possibly impossible to find purely amorphous material, and it may be purely impossible to find purely crystalline. So you're going to have a material that is crystalline. So when we look at the range, let's say between 100 to 0. So most material falls into that. Looking at materials like polymers, they are in between. Some of them, we have crystalline polymers, we have amorphous polymers, and then we have a lot of other different materials. And who are the people that will need this information? This will be very useful for solid state physics, especially those people doing experimental physics. And then it will be useful for medical physics as well, chemistry and biochemistry. And also, we can use it for material sciences. So what is X-ray? These are things that most of you already know, so I'm not going to spend a lot of time on that. So we know that this is X-ray. The difference between that with visible light is we can see that the wavelength is kind of smaller compared to that visible light. But it has more energy, and then it is more penetrating. So if it can penetrate to the core of electrons, it has the ability to ionize that specific material. And when it does that, you can get valuable information. Now, let me look into how the X5d works. Very unfortunate, we do not have X5d machine in our department. However, we can have a picture, which is not very clear there. But this is basically the way this works. So, we've got a material somewhere. So here, we have X-ray tube. And this X-ray tube is where these X-rays are generated. So the X-ray tube, it has two different electrode material. It has the anode material. So this one, it has the anode, it has the cathode. So in general, the anode is made up of materials like copper, molybdenum, and iron as well. So electrons are used to bombard these targets. And when electrons are used to bombard them, they are able to generate beams of X-rays. And the X-rays is being passed through collimator. This one narrows this X-ray that is being generated from that, and then it passes through to the sample. Depends on the machine. The sample could be like this specific machine. This machine here, you see how the sample is not rotating on this particular machine. And the machine they have in CIU, the sample gets rotated. So when it gets rotated, you find those X-ray coming out, and then you can actually pick the angles at which each one of them can be seen on the systems. Now, the kind of diffraction we have is generally a constructive diffraction. Let's see the main component of what happened. Most times, you find atoms, materials So this is atoms. For a crystal materials, they have repeating units of atoms. For non-crystal materials, the atoms are not repeating. They are in random arrangements. So when you pass light to it, you see this one here is the planes of the atoms, and then when the X-ray is actually passed through it, it's able to diffract, and then the angles of diffraction is actually obtained. Now, in order for this to be called an X-ray, for it to obey the law, it has to follow the Bragg's law. So the Braggs, these are father and son, they are physicists, and they gave this law that for any XRD to actually pass, for any XRD diffraction to be obtained, this kind of interference must be generated. And what is this? This is the wavelength that is used from the radiation, and this one is the distance between this plane, the distance between the two plates, that this one, and then this is the angle we have. What are the information we are going to get specifically today? From XRD, we may be able to know the kind of phase that we have in our material. Each material have different phase. When we say phase, we mean things like calcites, alexandrites, different phase. They have different structure. So if you have a material, when we pass it through XRD, we may be able to see, oh, my material contains this kind of phase, that type of phase. We may be able to know how much of those phase we have in the material. We could find what we call the material crystallinity index. So if you have two materials, you want to check if this material is amorphous or crystalline. Even you know it is amorphous, but what is the percentage of crystallinity or amorphous level in this material? Because the percentage of crystallinity affects the properties. For instance, you are preparing a material, you want to use it for adsorbent or something that can swell. Or you need a material that have high mechanical properties. If you have a material that is purely amorphous, the mechanical property is going to be very low. But if the material has high crystallinity, it's going to have a temperature that is high. Meanwhile, for you to degrade it, you need a lot of energy. So more crystalline material is more stable than less crystalline materials. We can get the lattice parameters from the materials. We can look for the average crystallite size. So we prepare the materials. We want to know what is the crystallite size. We can get it. We can also look for the strain. So when we prepare material has stress, it has strain. So we can use the XRD to probe the mechanical properties of the materials. So today I intend to go through every one of them. So it's going to be more of data analysis, and we will get an XRD data, and then we'll see how we can actually do all these things. One other important thing is we can also get the density of the material from the XRD. We can also know the surface area of materials. So before I jump into the data, it is very important to have a brief knowledge of what a crystal looks like. These are basic crystals. And these basic crystals we have different forms of them. There are actually 7. And the difference between them is the length and the angles between each of those unit cells. So if you look at this A, B, C, that represents the length of each of the unit cells. this unit cell, we have the simple cubic and all those ones. And if you look at something, for a cubic material, basic mathematics, we know that all the lengths of a cube, they are the same. And the angles between each of the face, they are the same as well. So how do I know what material I have? It means that when I have a material and I have XRD data, I need to find the lengths. So if all the length of my material is the same, and if all the angles is equal to 90, I can categorically say that my material is a cube. So these are the things. And we have some other formulas there to find the interspacing. And those are the things we are going to do. Now, this is what an XRD data, the pattern of XRD, what it looks like. So you will see different ones. So I've seen it in a lot of papers. People just say this material is amorphous, this material is crystalline. But what is the level of crystallinity? What is the level of amorphous content in this material? If I could ask the audience, which of the material is amorphous? For those of you that have any knowledge about it, not Ojam. Any person? Which of these materials, let's say, which one is the most crystalline? I've got 1, 2, 3, 5 marks there. Jahid, any help? Second one. The most crystalline. Out of 5.
Most amorphous.
1, 2, 3, 4, 5. The most crystalline is which one?
The top one is more crystalline and the bottom is more amorphous.
Okay. All right, let me limit it to these two. Between these and these two, which one is the most crystalline? Yeah. A is the most crystalline. Why do you say that?
Because I think in crystalline, they have more diffraction, exhibit less diffraction.
Okay. If you look at it, just looking, I'm going to pick this one to be more crystalline because of those sharp peaks. Those ones that you have those sharp peaks, these are the crystalline region. So I will, just looking, I will say A. But when we go to the data, it may not be. So we have these two materials. So these peaks that are sharp, like these ones that are sharp peaks, they are crystalline points. So this region shows that this material is crystalline. This one here is actually the XRD of chitosan. And this XRD of chitosan here is actually less crystalline compared to this, just looking at that. But how much crystallinity? What else can I get from that? Now, let's look at those graphs there. You see almost all these graphs here. Do you think any of these three patterns, do you think any of them is amorphous? Because if you look at here, you see they are broad peaks shows amorphous region, broad one. But if you look at this one, you couldn't find any broad. So are you going to say these three materials, they are purely crystalline?
Can be mixed.
Yes, actually it's mixed. So the parts that are peaks, they are the crystalline. The other parts, they are the amorphous. And then we're going to now check. So what we do is, all those small peaks you see, all these small peaks, we're going to make it bigger. And we're going to look each of the things inside this. And we'll find the area under them. So we will use this and we will make it a much bigger one. And we'll be able to find more information. So before I go in order for you to actually characterize a material using XRD, let's say you have your material, like Oda, you have your material, most of the students, you have the materials. So please, you're going to have a look. Anything I do now, you will need to repeat it with your material. So you are not going to come to my office and disturb me. So I'm expecting that today, you will learn how to actually characterize the material. So we have prepared a lot of material, we send it out. We want to get a lot of information. We want to get the crystal information from that. So what are the things you will need? Basic softwares like Excel. You need it. And you must know how to use Excel very well. We will need another software which is called Origin. And then we will need Prof. This is another software. I'm using this opportunity with the chairman of this department. Some of this software, they are expensive. Expert, I bought it $2,000 and I have to pay $2,000 every year. Not all the students are able to do that, but they have an opportunity for departmental. So if you tell them you've got like 20, 30 students, there's a discount. So you can provide it for the student, they will need it a lot. And then we're going to be looking at March. This is another software. None of the software is free anyway, but for the meantime, the student can download the trial version. And for those of you that don't have the HRD data, if you are very much interested, I will send you. Then you will try to replicate the same thing I've done, so that you know that you can actually deal with them. This is another software, Festa. So you're going to be like, oh, are we going to buy all the software? Because if you're going to probe any material, it's not one-day job. I will spend time, sometime, 3 days, to characterize just one material, to get the valuable data. So when you read the papers, you just, oh, this, no. The energy that is put in getting that paper is not free. It's actually purchased. And then we will use this one as well, Crystal Impacts. I have selected the following software because these ones are very easy. You don't really need to be in computer science or computer engineering to use them. These are just basic things that you can use. So let's go ahead and start to use them. So that is it. So what is the first thing we are going to do today? We are going to see how we can actually know how much crystalline, how much amorphous do we have in a material. So when you're writing your papers, you can categorically say that this material is 46% crystalline. So if you try to modify the material, you can see the difference in the crystallinity. You can talk about this material can swell, it can absorb, it can do this. So I will jump into data now. So the first one is origin. So let me put it so that the people can easily see that. So we have origin. So this is what origin looks like. That is the full name. I have it somewhere there. This one, origin 2022. So you can always download it. So this is the interface of origin. It looks exactly like that.
So, excuse me, Akeem.
Okay.
This is not a program specific to Excel.
No.
It's just
So,
a graph program.
It's just a graph program. So this one, the advantage of this software is, for anybody that will deal with material, is variable. As you see this, you can probe XRD, FTR, anything, and you have the capability, depends on your knowledge, to improve this software. For me, I have loaded extra accessory. I have about 50 accessory from XRD, FTR. It makes my life much easier. So I can easily do many things. The software allows you to add anything into that. So you can use it for anything, not just for XRD, for anything you would do. Whichever department you find yourself, you can use this. Now, I have opened that, so let me just upload one of my data. Where's that? Okay. Here is, we have some data of XRD. Generally, when you get XRD, so one thing I will tell the students or whoever is going to do this is this. Some people, when you ask them to give you XRD, they will just send you the graph. Please tell them, you need the raw data. Just the graph, you are just going to be looking at the graph. You cannot do anything. But when you get the raw data, you can draw yourself, you can do several things. And the things we're going to be doing is, I will take this data. The first data here is the angles that the XRD is being diffracted. That is the first one. And the second one is the intensity that is being generated. So I've got a lot of different materials. Some of these are things that we've already published. Later on, I will show you this in our papers, so you will see them. So I picked the first one here for, let me go to, so I'll pick the first material here. Let's see, I pick this, LDH voucher, and then I copy that, and I also copy both of them. I'm just going to put them into the program. So when you have it, just open this program and just paste it in the program. So I've got the data in the program. So then I can draw it. So for me to draw that, it's easy to use. It's asking me to pick. See what happened? When I pasted this data, there is one cell that is missing. So the program couldn't understand what to do. So when you're putting your data, you have to put your data from the first cell so that it can understand what happened. So let me try to delete this cell. So they are on the same level, the first cell. Then I can go ahead to plot it. So I will pick my X and Y. It gives me this, but this is not what I want. If you do it like this, what I want is to give me a pattern like this. Let's pick this one from this Excel. I pick these two from this Excel, and then when you look at it, this is what I want. This is what Excel gives me. This is XRD. Okay. So I pick this, I pick these two, and then I will have the center. So if you don't pick them, you just have a normal straight line. So you need to pick the data so that the system knows what you want to do. So I have picked this data, and you can see that is this material. Before I do the amorphous crystalline, can somebody tell me how much crystallinity will this material have in between 0 to 100? Selma, just give me a number. Give a number. 60%. So she says 60%. Okay. So I have obtained my data, but the first thing is this. When you have the data, can you look at this data? Look at the edges. Are they all on the same line? The edge, I mean, if you look at something below here,
You mean the baseline?
the baseline, they are not. So it means we have to correct the baseline before we process it. That is the first thing. So now I'm going to correct the baseline from this data. So I will just pick the same data here. Then if you look at those tabs, you find something written there, analysis, up there. So we can see analysis here. So you can just pick the analysis. So under the analysis, we have various things there. So we are interested in baseline. So we're going to go straight up and pick the baseline. And if we pick the baseline, we also have multiple things. For now, I'm not interested to pick the peaks. I'm interested in the baseline. So I will go ahead and do this one. So when you click that, then you have open dialog. So go ahead and pick that dialog, and then it will give me some other information when I pick that. So it gives me the following things. So these things it gives, what I want to do is to correct the baseline. So I will go there and subtract the instrumental from that place. You can see subtract baseline. And then I will select that to subtract it. Then you're going to click to finish, to next. Now, when you click to next, it gives you a constant. That constant is based on this software. But what you want to do, you want to take the baseline from this extreme to that extreme. So you're going to select user define, your own, not the software. So you go down here to the constants, and you will see here, which is a user define. Then you will pick that. So now we next it, and then we next, and we finish. We have corrected the baseline. Do you see any difference? Honestly, you can never see difference, but I will show you the difference. So this is the ones I have processed. So let me show you the ones that I've corrected. So now, this is my original data. The first two tabs are the ones that I processed. And now, these next two are the ones that I've removed the baseline. So I can go ahead to do things. It's always plotted 2 theta. And the unit is actually degree. Then I have the intensity. and then the unit is actually arbitrary. Then you can write whatever comment you want here for your own sake. So I can just write this one to be baseline corrected. So I've got that. So now for us to see the difference, I will pick both of them. I'll pick the first one. I will pick the second one, the one I corrected. So let's see the difference. So the red one, can we see the difference? If you don't see, I'll show you. So you can see the red one, it's corrected, and the black one is not. So the next thing, if you're going to process your data, you will now process from the one that is corrected. So if you don't process it from the corrected one, what you're going to get will be wrong. So from now on, I will go ahead and deal with corrected one. So let me deal with it. Do anybody have a problem in using it? It's very easy. Do you understand what I've done? Just plot your graph. I can repeat the process, it's quite an easy one. You see, the first thing I did is to plot these two. And to plot, you see down here, there is different plots. So you can just pick that, then it will plot it. So when you plot it, you can actually expand this. So you see a lot of graph there, but any of the graph that is outside is the one the system sees. So this is uncorrected one.
May I ask one question?
Yeah.
But when you get raw data,
Yes.
okay, that's correct. You also get the plot from
Yes,
the
I have,
place
yeah.
that they are
Yeah.
doing the analysis for you. So that plot that you take, they send you, you mean it's not
It's not corrected, yes. So when you look at it, like each one of them, we have the raw data as well, and the plotted one. So you will see that it's never corrected. So the ones you have,
Other instruments computerize them to do all those corrections. And
the
everything.
instrument have correction,
Mhm.
but the people you send to, they are doing their job, just characterize for you. So if you are in the lab, you want to do it, you can do your own correction. But if I look at the graph, I see one of the legs is flying off, this is not corrected. And any data I got there is going to be wrong. So from when they send it to us, we have the one they plotted. And then when you use the data, you check them. You will see, because this software also have, you can check graphs.
So, for example, can you calculate what's percent error?
Yes, yes, yes. We can.
That they corrected and
Yeah.
incorrected.
As yesterday, I think almost 6 or 7 or 8%.
Yes, from 36 to 42.
Yes, almost 8% difference.
8%.
Yes, for crystallinity. But when you get to the density of the material, almost 20% difference. Because the density peaks on, you don't pick everything for the density, you pick more of the crystalline parts for the density. So when they are not corrected, the difference when you're trying to get the density is much. But for the crystallinity index, about 6 to 8% depends on the material.
Acceptable, I mean,
Yes, depends on the leg.
yeah.
Yeah.
It depends on your purpose.
Yes. So that is it. So this is the raw data for anybody that wants to follow it again. Just pick that raw data, go to analysis,
Hocam,
and then you will go to baseline.
can you just zoom in
Zoom, how does it zoom? How can I
from the
zoom it?
right corner there?
Follow the maximum peak.
This one? Yeah. It is only this one that zoom.
Not this 200. Those other
Okay. Is this okay for you? Or what do you want to see? Those things I'm selecting, right?
Yes.
Yes, sir, the things you are selecting, it's not very visible.
I couldn't know how to zoom from this computer.
Do you have the control for the projector?
No, I just have for my computer.
It might be possible to zoom that
Yeah.
a little before.
Can you write manually 125?
Yes. I can write manually if you want. Where is
And that
what do you mean?
yeah, there. I think you can write.
Yes, I can write. But this we just, I believe it will. The problem of guide, I believe, is the files, not this one.
Yes, with the toolbar.
Yeah. Okay. But Jahid, can you see this analysis? Can somebody give him double glasses?
It's all a blur. And I haven't started printing yet.
Oh, Jahid, so I pick this one, and then I have analysis. So when I pick the analysis, can you see that? Then there's a peaks and baseline. Right? So after the peaks and baseline, there is peak analyzer. And then there is open the dialog. So I can just open that dialog. So this dialog, you can do different things from this. So, but the first thing we're going to do is to correct the baseline. So I'm going to subtract. I will select that. Then I'll go ahead to do next. So when I get to next, I want it to cover all the extremes from one end to the other. So I'll go to choose the mode. And the mode is going to be user-defined mode, the second one. I'll select that one. And then I'll click next. And then next. Then I'm done. So with these ones, the baseline is corrected. So you can just minimize this graph from this edge. And then you can see that the baseline is corrected. And for you to see that, you can just look at your data. So I have done 2 baseline corrected. This is the first one, these 2. And then the other ones are here. So this is what I'm interested in. I can delete these ones because I've done them already. I can delete all these ones. Oh, I delete that one. Done.
Akeem, is it possible to correct the corrected one?
No, if you try to correct it, you will see that it's 0. So we did that. The one that is already corrected, we got one XRD from Iran and Iraq. They have already done the correction. So when you do it, when you check the constants, you will see 0 there. It doesn't have any like that. So from there, we know this one is corrected, this one. If it is corrected, they will have 0 or negative values in the constant. Meanwhile, we can use this to correct FTR, UV, any of these things. You can correct it with the whole system as well. And there's different mathematical corrections that you can use, depends on whatever you wanted to do.
What
So,
if you like the real stuff? What if you like the real stuff? You don't want to correct.
It depends. If you don't want it corrected, I believe that in the date in the report, one should mention that this is uncorrected data. So I like to give all the information on my home paper. So that people know.
All correction is mathematical trickery.
Yes.
So it may be doing something that you may be losing legitimate information without realizing.
Exactly. So here I am choosing Gaussian.
I'm sorry. So maybe instead instead of, what I think is, instead of reporting that this data is not corrected, maybe it's better, I think, to say that it is corrected using such and such software. Isn't it
Yes.
so? If you don't say so anything, it means that that's what you got from the instrument. You
Yes.
have to mention that.
Exactly.
But
So,
if you are doing something,
yeah.
because I think maybe if you don't use origin and you use something, another program, maybe you will get something slightly different. You have to mention which
software, yes.
you have used for.
Like I have other software, and I've tried the same data for about 4 different software. The difference is small because you will choose the math to do the correction. We have polynomial correction, Gaussian correction, Gauss correction. So if you select all your material to correct based on this mathematics, the difference based on the software will be very small.
But I agree with Mehmet when you were saying that maybe you don't want to use anything in the original spectrum. So that's a choice.
Yes. So it depends on the person, what you are going to present. However, the person will need to state it. So like us, when we do the papers, we write this is used for that.
I see.
So if any
You
person,
mentioned that the data was corrected using
yes,
such and such.
we had a problem. I published a paper about supercapacitor. One of the reviewers is very good, and he asked one question in the reviewer. He told me, you deconflate your peaks. That I do not agree with you because he said pyridinic nitrogen, the peak should come before another nitrogen. And he said, if you can send me the raw data. So when I was doing my revision, I sent the raw data. So he made the plots. There's a difference there, but I told him I've used this software. So when he used the software, then he agreed with it because it will give you the same data.
So if you don't mention that, people who are working on the same subject, when they get something different than you reported over there, then
Yes.
yeah, they may ask
Wow.
that question.
Exactly. Yeah.
Similar things are happening actually in physics, but those are numerical things coming from the mathematics.
Yes.
And they're all approved.
Yeah.
The only thing that I agree with Roger is whatever technique is used,
Yes.
it must be mentioned.
Exactly.
And even there are some researchers that they compare the methods.
Yes.
But these are all approved methodologies.
Of course.
That's why they are now in the program.
Exactly.
And even, this is what I know, for instance, that FTR here, it is using Fourier transformation.
Yes.
Even the machine itself is correct.
Yeah.
Yes, of course.
They have its own correction
baseline correction.
methodology. Otherwise, there are noise. I mean, some unwanted things. By default, it eliminates them. Nothing is fully 100%, let's say, original.
Yeah. Okay. So let's quickly, because of time. So this one is the corrected one, and I will start to process this one. So how do I process it to know? So the thing is, if you want to calculate the percentage of crystallinity, can I write somewhere? So the percentage of crystallinity is going to be the areas of the crystalline sections. So those sharp peaks, I need to look for the areas. And then I will then divide the areas of that crystalline with the total area, including the amorphous and the crystalline. So areas of amorphous, yes, total area. Then you just multiply by 100, you can get the percentage. So let's go ahead to use this formula, the percentage of crystalline and the percentage of the total area down there. So let me pick the crystalline ones. So what you may do, some of the things I've done to make my life much easier, I created an Excel whereby I just put the areas of crystalline, area of amorphous, I can do the calculations. So let me pick those areas. Now, I'm just going to select this again. Then I'll go to the data analysis, the analysis as well, just like I've done before. I'll go ahead to the peaks and baseline, the same thing I've done, but what will be the difference? In this time, I'm not correcting because this is corrected. So in this time, I'm going to integrate the peaks. So I will select the integration. That is the first thing. So I have selected the integrate, and then I will go to next. So if you go to next, you will see a constant there. So I will pick the constant because I will need it later on. So let me pick that constant. So let me just open this file. I have put that constant somewhere there. Okay. So the next thing I will do is I will go next. And then I will go next. So in this case, I want the software to find all the peaks automatically. But you see, when you look at the peaks, if I try to bring it, if I ask some of you, I'm sure it will be wrong. How many sharp peaks do I see? How many? 10. Based on your eyes, it's 10, but the software knows that it's more. So the software is going to pick anything that looks crystalline. So if I just say find it automatically, let's see how many it can find. So here, you see it has selected 0, but I want to find now. I found it. It finds 15. So automatically it indexed them. So, but when I look at the 15, let's see where are the ones.
Are you selecting the threshold?
I'm selecting, yes, the one that has intensity above the normal threshold. Anyone above that normal threshold that looks like a peak, it's selected.
So the instrument chooses the threshold.
Yes.
I mean, the software.
The software chooses a threshold.
You don't mention it.
I don't mention it. So, if you look at all this area,
Can you change the threshold manually?
yeah, you can change it actually. In fact, for me, I don't try to pick this automatically. There are some of the peaks I don't consider it valuable. So I would rather pick it one by one myself. Because when you look at this, I found this one very reasonable peak, isn't it? This small one, but it doesn't select it. And then let's see all the ones. See, it doesn't select another 2 peaks somewhere there. It couldn't select this one. It did not select this one. What about these 2 peaks? Although in a real sense, the X5d between when you go to 60, most of the information after 60 is really not very valuable much. So, but then you could select it, it all depends on you. So now, if you look, some of them, it selects more than one. Because, let me show you what happens, why it selects more than one. Okay, I'll show later. We can actually, if you take this peak, I wanted to see what happened to this peak. You see, if it's even 3, but we cannot see it. That is why this instrument is able to see them. And they are peaks. So in that place, actually it's 4. But what is the difference? Is not so much, but it counts. So that is why that is it. I can go ahead to say that, okay, I don't want it to select those peaks. I want it to select myself. So if I want to select myself, I can clear all this peak. So I cleared all the peaks. So I will then select myself. So to select myself, I will just click add. You see something add in that place, first one. So I will select that one. Then I will start to select the peaks of my own. So I can go ahead and pick the first one. So when you put there, there's a sensor there, you just double click it. So when you double click this one,
Okay.
yeah.
Is this a pure compound? Is it a mixture?
This is a mixture. This is a palm seed. Palm seed. This,
Palm seed,
yes. We converted it into boucher. We calcinate it, convert it to boucher, and then we mix it with inorganic material. So it has, we know from the palm seed, the major component is carbon. So that is why you find some of those amorphous parts there. Then, because we combine it with inorganic, then we have those ones in that place. So what we are trying to do in this work, we try to look, what is the composition of the boucher? What is the composition of inorganic? We have done that theoretically. But then with this XRD, it can help us to actually see that our calculation theoretically makes sense. Because if you're adding 1 gram of this one with 1 gram of this one, when I do this quantitatively, I'm supposed to see 1, 1. But I can check the phase of each one of them. If it is close to 1, 1, it's okay for me. But if I have 0.2 and 1, then something is wrong. So I pick this particular one. Then I'm going to go ahead and pick this second one. I can pick this one. This one is enough. If you like, you can pick others. It all depends on you. Then I have to pick this big one. So I pick all them. I pick 7 actually. So after you pick them, then you can tell it's done. So 7 picks have been picked, as you can see it here. And then I go to the next. So now, when I go to the next, those picks that are picked, it actually integrates it. But I need those things to be symmetric. Both sides need to be the same. So what I'm going to do is, I will activate this. So look at here, there's something they call adjust the preview. So I will pick that one. So if I pick it, then I'm able to, because if you look at these parts, you will realize that it picks some parts that is not crystalline. So I have to adjust it myself. So that is where the business comes. So let's go. So this one, I believe is off feed. So I can manually just make it to cover just that part alone. Then this one is too big. All this part is amorphous. I can just take it to cover that part. Then this one is too big as well. I can take it to cover this. I can take it to cover this one. Then this is okay. So it all depends on you, how precise you want to do. You can always go ahead and do all those things. And then this one goes to this level, and then these ones. This one. Okay. So I have picked those regions where the full width started, you have to pick it. So what I wanted to do, I wanted to find the area under that part. So since I've done that, then I will just click finish. So you can see all the handles that I've selected, and then the areas that I picked, 7, I have it already. That is the crystalline. So let me go and pick my area. So just minimize this one. Minimize this. You come to your data. You can see your area 7 pixels. These are the 7 pixels, right? And this one is the area. This one here is the area of that part. So I can just take that area for the crystalline. So I'm just going to pick that area, copy it. So I have, where are you? I made an Excel. So this Excel that I made, I have made like a simple calculations into it. I can just dump this data. So here I'm in this first part. So I wanted to put the areas that I copied from that place. So I think I've copied 7 of them. So 7 should stop here. Let me first delete it. This one. So this is the 7 peaks that I have. And then I can sum them together. Just add all of them together. So I made a calculation up here. You can see this one changed when I dropped them. So this one, this is the calculation up here, if you can see. It's just the sum of everything. Just simple math. So I have the area. Go back. I've done something wrong. Okay. So I have sum, and I'm summing from A12, and I'm going to A18. So that is it, right? No, this is 11, not actually. This is 11 to 18. You say what?
From 12.
Okay, from 12 actually. To 18. Okay. So I have all the areas. Then I will now go and pick the total area. So let's go ahead and pick the total area now. So remember that we're going to be using the one that is corrected in this case. So that's my corrected one. Okay, it's corrected. Now, I wanted to pick all this area, including, so I can just select that. Then this time around, I don't want to go through long process. I'm going to go through gadgets this time around. So, let me pick this gadget. And when you look at the gadget, you see also integrate, just like I've integrated. So I select that integrate, and then under integrate, it shows me which kind of integration I want to use, mathematical integration. But remember that other time I pick a particular constant when I was doing that. So I'm going to put in that constant value. I drop the constant value somewhere here. And then I will just put it here. So I check everything is okay. Then I want to keep the shading to show me the area. And then if I'm done with that, I'll just press OK. So it picked that area, but I want all the areas. So I'm going to now pick all the areas. I will just stretch it to the edge. I will stretch it to the head. And here is the area. So you can see the area here. So I can just pick, this is the area of all these. I can pick it and go to the Excel. This area of everything. So I can just dump it there. So 42.4%. So Simon, you are owing me ice cream. So that is it. So I have the crystalline parts and I have the amorphous, and then I just divide that by that and I have 42.5%. So I can always report it. So what we did in this material, we have the voucher. We discovered that the voucher is more amorphous than when we mixed it. When we run the voucher, we got about 68%. So when we had that material, we got 20-something. So we can check to see if the ratio we had experimentally actually conform with that. So this is how we can easily deal with crystallinity. So, do anybody have a question?
What if we want to simplify things and we just use peak intensities?
Peak intensity. What do you want from peak intensity?
Crystallinity.
From the intensity alone you can, because it's the intensity goes up, but from the base you have to consider the full width, height of everything. Just the intensity he will give you wrong. He did that yesterday. So yesterday I gave him homework to do, and he picked just the intensity, but it's totally wrong because you have to. No, the difference is much, my dear. You know, when he did it with just intensity, almost maybe 6 or 7, 30, you got 30. So that is it. So you have to consider all the area on that.
Yeah, that's correct. Yeah.
Yes.
I just wanted people to realize that when you do it with peak intensity, it should carry more error.
Yes. So that's it. Do you have any question? Good. So I believe that we can use this software, any one of you. Jahid? Perfect. So what is the other thing that we may learn from? Since we have gotten this, we have other things which we call the D-spacing. I showed you the other time about the D-spacing. So space between each of those. And we can easily calculate the D-spacing using the Bragg's law. So this is the law that we can use. This is the formula to find the space between each of the atoms in the crystal. So this is actually coming from Bragg's himself. So the wavelength that is used to bombard the material, and then the sine theta of that. So how do we do that? If you get your XRD, they will tell you which wavelength is used. Commonly used is copper. And copper alpha, this is the wavelength somewhere here. This one, you can see it. So when they send your data, you will see the wavelength, they will tell you. So that is it. We have different materials. So whichever material that is used in your stuff, you will use that wavelength. Now, since this is what we want, to do, it means that we need to find just the 2 sine theta from that. Now, these things you have here, I have already know the areas. Oh. So let me pick the sine theta since I need it. I will need the position of each of the peaks from that place. I need a position to calculate it because if you look at my formula, it says 2 sine theta. So I need the position. And how do I do the position? So I have that, and I have this. So this is the corrected one. So this time, I just want to see what is this. This angle here, there are 2 theta, the angle below. And this one is intensity. So I can just automatically find all these peaks at once. So let me go to the analysis. But this time, let me do fitting, or let me go. I can smoothen it or I can fit it, any one of them. We can actually do anything with it. But this time, I don't want to do one by one. I want you to pick all of them at once. So I'll go ahead and do multiple picks. So baseline, multiple picks, and I open the dialog. Now, I can pick it differently. There is different mathematics there. So from various theory published papers and from Mr. Bratz that makes this law, he suggested this one is good, Gauss. So there's a lot, so any person can try different ones. So I'm just going to leave it the way I've selected it, this one, like that. And if that is the case, I will just go ahead and do this. So I will start to I just pick this one. I get it opened. So after you get it opened, then I want to also integrate it. So you will see the last one here. It gives me full integration and convergence of the peaks. So please go ahead and then push it up. So if we start to integrate, you can see something is done at the other side there. So it is done. When the work is done, you can see that it says the parameter is forward. And then that is done. So all the peaks are selected and the cumulative peak is here. So let me see the data. It's asking me, do you want to switch to report? Yes, I can just look at the report immediately. So if I look at the report, you will see all those peaks that is automatically just come down here. So these are the peaks of those 7. If you look at it, I will show you. So be sure that it's correct. This is 18.3, the first one. So go back to your graph. Where is the graph? Somewhere here. So this peak, it says it's 18 point something. So let's look at it. So this place, it has screen reader. If you can see that one, it can have annotation. You can point it, it will tell you what the peak is. Or you can use this one, data analyzer. So if I pick this one, just go here. You will see the peak down there, the green one. Do you see? Here. You will see it is 18.33. So that is it. So it's the same thing that I have here from the data that I've done automatically, 18.3 something. So I can just pick all these places and then I will copy them. So these ones are the angles which they appear. Then I will come to my graph here. This angles is all this angle that appears are 2 theta. So let me delete it from our data. So I pick the 7 peaks, and I try to paste them. Although, what did I do? Did I pick all of them? Pick all. Huh? The size of pasting. Okay. Anyway, so let me just pick one of them. So I have 18.3 for instance, and then that is the first peak in that particular place. Then here I have 30.16. And the last one, I think I have 35.5. And 54, 57. So just pick each one of them. So these are all the peaks that are 2 theta. 7 of those peaks. Now, if you look at the formula says that we need to have the wavelength divided by 2 sine theta from the Bragg's law. So, since it's 2 theta, I need 1 theta. So I have to divide this one by 2 to have 1. So that is what I do here. So the formula here is going to be, let me first delete everything here. Okay, so I'm just going to pick this one. Is in E, and it is E11. That's one, and then I'm dividing it by 2. So that is what I have. I can just cover it up. Just double click this one. So it gives me all of them. So I have done for the theta. Now, Excel cannot process degree. So you have to convert the degree to radians. So now let me go ahead and convert that degree to radians. So I have sine here. So what I did is very simple one. Look at the formula up. If you can look at the formula, let's make it so that we can get to see how it's done. So I clear all this. So that particular place, I want that theta. So I'm saying sine theta. So I pick the sine, but then I need to convert it to radians. So I need to do radians. This price radians. So it goes radians, and then you pick which one, which is actually F11. So that gives me the value. So this is converted to radians. Just double click that, it will give you all the values. Then I will just need to multiply this value by 2, this second column. So this value is then multiplied by 2, like that. So I have all this. So the equation says this one, the lambda, the wavelengths, divided by 2 sine theta. So I have it in this last column. So that is what I did. The lambda is 1.506 in this. This is in Armstrong. And then I'm dividing it by this, and I have this interplanar distance. So I can take the average for all of them. So if you're going to report it, because you have a lot of peaks, so you take the average of those peaks and then you report it. So that is it. Do we have any question about this? This is very easy, just using the formulas to find the distance. Now, what about the crystallite size? I'm able to do that as well. So, crystallite size is different from particle size. The crystal and the whole the crystal, when they join together, they make those particles. So you are just going to get one size of a crystal. So if you want to calculate it, because we realize that the crystal size have effects. We have some materials that are magnetic. We realize that the one that when the crystalline size decreases, the magnetism also decreases. Also, we have the one that is swelling. When the size becomes like the work of the guy from Iraq, I forgot his name. Zira. So we have.
Are those in Amsterdam, right?
Yes. So these ones are in Amsterdam.
We are in Amsterdam.
Yes. Like that. Yeah, in
Can
Amsterdam.
you make it a bit bigger?
Yes, Zira. Yes. Okay.
Do you take the average of those?
Yes, if I'm going to record all of them, all the interplanar space, then I take the average of them.
Do they refer to the same?
Material or different peaks.
This is the distance between
Each
two
atom.
planes.
Yes.
Do you take their average
Yes.
as
For that particular material. Because the material, for instance, this material contains 8 atoms according to the cube.
is this material a cubic crystal?
Yes.
It is a perfectly cubic crystal.
Yes. Later, not today because of the time. There's another software. When I just upload this, it automatically tells me if this is a cube, if it is tetragonal or this. And since I know that for a cube, all the lengths must be equal, all the angles must be equal to 90, then I can prove it from this. I will find each of the lengths, and if all the lengths are the same, and the angles are equal to 90, then the software and my calculation is correct.
Okay.
It is fully fractional.
Yes. William?
Yes.
Can you explain why this interplanar distance is decreasing with different?
Okay. If you notice this one, if we look at this one, this itself, we will see that these have different intensity. So this intensity tells about the number of atoms in that part. So when we bring each one of them out, for instance, if I bring this one out, if you do more, if I take the breadth of that one, compare it with the breadth of other ones, you will see that as you are going down, the angles is increasing. That the interplanar also decreases as well. So that is it actually. Now there's one thing you guys need to know. XRD normally it has instrumental contribution, which is called broadening. So after we have different scientists, Scherer, David Scherer, all these things, they calculated the strain distress. However, after many years, Williams discovered that What they didn't consider the instrumental contribution. So what I do basically is I also, we can calculate this string according to the first scientist. We can also calculate it based on the other scientists to see the contribution of each of these instruments. If instrument is contributing to the broadening or not. So that is it. So you can probe any of those peaks anyway. So these are the interplanar distance, and then I can take the average, I can report the average. So when I'm reporting in my papers, I'm writing average interplanar distance. So they know that I've taken all of them. However, I've seen a lot of paper, they just pick the most intense peaks. So we have done that in our paper as well. So what I wrote is, I said peak 311. This is it. So if you are requesting for my data, you don't get lost. So that you know that I picked for just 311, not all of them. So if you're going to take the average, write it average, but if you pick one particular peak, you have to mention which plane you are taking. So, and these are the ones I've gotten. So here, we wanted to calculate the crystallized size. And to calculate the crystallized size, this is the formula from here. This formula, we use it to calculate the crystalline size. This is given by David Scherer. And that K is the diffraction order, which is generally taken as 1. And then we have that one, which is the wavelengths. And we have the beta. The beta is the width of each of those peaks, the full width, height maximum, and then we have the cos theta. So since I already have my peak somewhere here, then I can have my full width. And I've done that. If you look at here,
What is the capital K which is in this?
a diffraction order, yes, it's generally 1.
But it has no unit.
It has no units. Now, let's go and pick, so I need this one, this beta, which is the width of each of the peaks. So I have already done that from the software. When we pick this, you will see it from this data here. So from this place, I pick the angle, and if you go a bit more, you will see it here. Can we see it here? FW something there. So you just pick that value, and that is the value. Yeah. So you can just dump the value into this particular place. So then when we dump the value, now these things are the peaks, they are angles. So I need to convert those angles to radians as well. So the same thing, when I pick this one, then I can easily convert them into the radian. So now I pick all of them and I dump it into this place. Then this is what I wanted to calculate. I wanted to calculate with this formula. And then I can use this. So that is what I did. What did I do? D is the crystallized size, which is equal to this formula. This one here is already 1. So that is 1 times the lambda. And I know that what is my lambda, but now, when I see the instruments, when we got the data, when they sent us, they said in their own instrument, their K is not 1. So they give us this graph, 0.94.
How do they decide it's one?
The machine. Yes. So when they send the data gives you some information about the wavelength, the K, all those things. So you just pick it from the machine. So I just pick exactly what is given to you. Each material has different. In crystal, the crystal structure, we have cesium chloride structure, they are generally like around 1. We have sodium chloride structures, they could be around more than 1. So they decide this value based on the crystal system. And whatever you do in this, the machine, it gives you whatever.
Also, they have reference.
Possibly.
And they compare the data size.
Yes. So from there, I pick the K. And in this case, since I want to find the crystallized size and I wanted to find it in nanometer, I decided to convert this one to nanometer from Armstrong. So this is converted to nanometer. So I have this. So in this formula, I just need to multiply, instead of multiplying 1 in this case, I'm going to multiply 0.94. In this case, with my wavelengths, that is actually here. And then this B, I have them here. And then cos theta. So I will just find the cos theta of that. Then I can find my crystallized size. So these are the crystallized size using that same formula. So I have all of them. Then to report them, you can just take the average. If you want to report for a single peaks, you have to mention you are reporting for this particular peak, like that. So that is it about this. Now, we have what we call dislocation. Dislocation density. And that's as soon as you can get the size of the material, you can see how much dislocation your material has. And the formula to do that one is this one. So you will see if you get one thing, you can always use it to get others. So this is the average that I've gotten for the size, and I just put that to calculate the dislocation, just 1 divided by d squared, 1 divided by the crystallized size. And then I can also find the strain. If there's a dislocation, it means there's a stress and there's a strain. So if I mix two materials together, I'm able to find how much stress, how much strain if I have this material. And then this is the formula to find the lattice strain. So just the same B you have gotten from here, divide by 4 tan theta, you will get the strain. So those are the basic things. So you will see that we have gotten 1, 2, 3, 4, and 5. So 5 different things you have already gotten from the same material, which you can report in your stuff. Now, we want to know, we said we have different crystal structure. We have a cube, we have tetragonal, we have all those things that are shown you. For me to know that this is a cube, I just need to look at the lengths and the angles, and I can find each of the lengths as well. So I made other ones. So I need to make it smaller so that you can see it. So I made other one to find the lattice constant as well. So I can find each of the lengths and the same information I have gotten before. Just the angles, the dispacing, and I can find for each one of them. So what I do is I will use that to find each of them. Then I will see anyone that conforms to my system. So this is the formula for a cube. This particular formula, I need to find one of the lengths, and I can find the second length as well. So, and this is the formula to do that. This specific formula, A is one of the lengths, so I need D. D is what I've already calculated already, and I need this HKL. So what is HKL? This is Miller indices. These tell about the plane directions. So 3 different plane directions, X, Y, Z. So now, if you look at what we've been talking, you will realize that you can't find these things. Let me show you what I mean by that. Okay. So there's a, look at this is one of our paper. This paper is published, I don't know, when we publish this crazy one. So this paper is published in 2022. So what did I do in this particular paper? I have mixed carbon with this inorganic material. So for me to be sure that this is correct, so I have to take the XRD of carbon alone. I need to take the XRD of that material alone. Then when I mix them together, I actually mix them in different ratios. Then I want to see what happened to them. And we got this XRD data. We got something like this. Is it too big? So this is what we have. So this one that is like, is it pink? That is the carbon. So if you look at that, you will see that it's actually kind of more amorphous than the others. You don't see any peaks. So for me to actually analyze this one is very easy. It will take just 5 minutes to find the amorphous, the same way I've done before. So these other ones, they are the ones, the last green one is the first inorganic material without mixing them together. And when I mix it together, but can we see any difference? I first see one difference. What is it? I see that this one down here, there's just this peak. You can see this peak. This particular peak. Every other thing is the same, but here, I don't have this peak here, but I have it here. So when I start to increase the concentration of the carbon, the peak of that one starts to grow more. Then I can run it, so I have different ones. Here I mix 1 to 1, 0.5, 2. Like that, I can see the difference. And then I can easily do many things with that. Now, you will be wondering, what are these numbers? 111, 311, all these things. These are the Miller indices. For you to identify your material, almost all the materials, they are in a database. So we have the diffraction database. Every person that have published paper, they deposit. So I published one paper. This material has never existed in database. I received an email from them. The paper was published, I don't know, maybe almost 1 year ago. They sent me email recently that you have prepared this material. It does not exist in this database, ICDD, International Diffraction Database. They give me specifications, send us all your real data. We are going to probe all the data, and when we probe it, it's okay, then it will appear there. So any person that publishes this kind of paper, and they use my material, they just need to index, they will give a number to my work, so they will just index it. So they don't need to worry themselves, because all these kind of peaks, I have identified them. So how do I identify these 311, all these things? Then I have to use another software to do that. So in order not to waste your time, it is easy to do. I don't know. So what I do here is, so this Excel, for any one of you that wants to do this, I will provide you with the raw data, the formulas, and I want you to try it to see that you get exactly what I've got. That if you are able to do that, that means that you have understand how to do this. So let me go ahead to see. So I've got some software. This one is called Match. So with the Match, I can easily look for the kind of phase, the quantification of the phase. I can actually find it. So Match, it just looks like that, but it's very powerful one. So now, if I want to do that, let me just pick one data to put in my Match. So First thing is this. Qualifiers. Okay. Yeah. Thank you, Jack, for visiting. Okay. Yes. Okay. So, for this match, first thing is this. The match, you have to put your data inside. And it will help you to tell which kind of phase your material, it can tell you if it is cube, it can tell you the composition as well. But then in the match, the kind of file it takes, it doesn't take Excel file or those things. It takes different formats. It takes this format, DAX. So what you do is, you get your diffraction data, you just paste your diffraction data in Notepad. So when you paste it in Notepad, when you want to save it, you will save it as .DAX instead of that. So when you do that, you can pick it. So now I have saved this material, this one. Then I can just pick it, open it. Then if you see, when I pick that, it's asking me which wavelength is used. So there's a lot of wavelengths, as I've mentioned. So this one, if you look at it, is 1.541. But when they send the data for me, it's not 1.541 they use. There's a lot of wavelengths there. So I have to select which one. The one they use for me is copper Ka1, which is the one just above it. This one. So I'm selecting that one. No. Where is it? I'm selecting this. Then it's asking me one question. Which kind of data is this? Is it a theta or 2 theta? My data is 2 theta. So I'm just going to put that into that place. So it just do this. See what it's doing. It's running it. It's trying to match it with anything in the database. And it's going to tell me what is possibility of this material. So it gave me a lot of things. So I will then select which one I think fits more into my data. So it's ranked it, the first one, you can see the number is 0.939. That is the most that is close to it. If you agree with it, but before you agree, you have to look at these things. You have to look at these things down here. You see, the ones down here, that red one belongs to that Franklin light. So you're going to see how much it matches with your material. I can see here, I have one here as well. It makes some sense. I see this one, it matches. I see this, it match, this match, that match. So, but that material also has some other things that I don't have. But if you look at it, it's kind of very high. So I can select that. I will just go ahead and select it. So then if you select it, it will suggest another for you. So then I have picked it. It's saying that it's like 100% match in that quantification. But I know that it's not 100% match. Why? This material we prepare, it actually contains iron, material, it contains oxygen, it contains zinc. But there's one thing that is material, nickel. But this one doesn't contain nickel, but it contains every other thing. So I pick that. So it means that about 85% of what I need, I can find it from here. Then I can look again. So all these ones, you see chromite, chromate, cochromite, these are faces. So I can just pick any face that I want and see how it matches. So you can go down and see there's a lot of them. So you pick whatever face. But what is the thing? What did I want to get? I wanted to get this HKL. So if you look up there, you could see something here like HKL. To get the HKL, because I will need it to find the length and distance. But if you download match, right, automatically you cannot have this HKL. you need to download some other software to have this accessibility. That software is called Prof. This one. You know? So let me just go ahead with this one. And then let me see if I can run Prof. So if you click on the Prof, it will try to be doing something. If it does anything correct, it will tell you. If it doesn't do anything correct, you can always refine it. So that side is telling you something. It can tell you it's not good enough. It can tell you it's good enough. That's high. So it tells me that my car is not very high. I need something that is high, as much as 10, but it's like 8.1. Like it's 1% match with what I want. Okay, that is good for me. Then I can find the HKL right here. That's it. So those are the HKL. I will just look at the handles. These are the HKL. You remember in my the graph, I have like 18.3, like that. So I will go to the 18.3, I will write 111 on top of that. So I will trace it out to all those ones, like that. And then, that's it. Now, I want this to suggest for me, which kind of crystal is it? So then, I've got this other one is two different software. So I can decide to run with the first one. Let's give you some suggestions. And I just press that. So I want to compare with all those ones, cubic, tetragonal, and all those things. Let it tell me which one it is. I just click OK. Yes. So his suggestion is that, look at the suggestion. He suggests that this material is tetragonal. Can you see something here? Where is it? Tetragonal. He suggests that it's tetragonal. And then these are the handles. He gave me the handles as well. You can see the handles, 90. And then, about tetragonal, two of the areas, the length, they are the same. One of them is not the same. So when you look at A, B, they are the same. And C is not the same. So that is it. This is suggestion. But I may not agree with the suggestion. I can rerun it to be very sure it is this or that. So in order not to take your time, do we have any questions? Because really we take some few practices to actually get hold of it. But when you get hold of it, you can do a lot with it. In fact, from my papers, from just one XRD, I can write about 20 different values, parameters that I can get from there. And that will boost the quality of my material. And I can automatically say, my material is this, my material is that. Because I'm able to prove it. Like that. So, if any one of you is very much interested, I will just tell me, I'll give you this data. You can download this software as a trial version. You can run it for like 30 days. Then try to do what? Get the crystalline information, all those things I've mentioned. Then you know that, oh, you know how to do it. So when you prepare any material, you are working on carbon nanotube. With carbon nanotube, you have to check what is it actually carbon nanotube you have prepared? Because carbon nanotube has a specific peak which the system will identify. So it will tell you, yes, this is carbon nanotube. So this is very valuable when you are doing anything in the lab. So do we have any question?
Thank you. What's the name of the that program? You said with the match, we can download the Prof, and there is another one.
Yes.
What's the name of it?
So these are the two. Where are they? These two. Trail 90 and Big 4. These two. This and that. So when you go to the website of Match, when you download Match, look for Full Prof. Download Full Prof. As soon as you download Full Prof, then Full Prof will now come with these two.
Is it freeware?
Huh?
Is it freeware?
No. But for 30 days.
Supposedly,
So do you have an idea if this is type of software that if you download it once to your laptop, it won't be downloaded again?
No. When you are on a trial version, you can download it as much as 10, 20. When you pay for it, when you are trying to pay, you will select. So for me, I decide to select 3 laptops. So I've got 3 computers, so I can use it on 3 computers. You understand? So if you are using it on 3 computers, the price is different from just one. If your department is interested, they can buy student version. So this one is always cheap. Student version is actually, the one I got $2,000, you check on the website, student $65. So, but I have to prove that I'm a student. They need my ID card, they need all this thing. So when I try to prove, they just Google the name. You are crazy, you are not a student. So that is it. So you will need this one. It's very valuable. There's one other one that will help you to quantify how many, when you prepare like Kaito-san for instance, it will help you to tell how many carbon, how many hydrogen, how many. So that one is this one. You can download it. Other time, I can teach you guys how it works. This one here, let me open it. This software, the name is, this is foolproof on its own. This one, the first one, foolproof suit. So this one, it has about more than 15 software combined together. So if you have any material you are characterizing, even the surface of the material, I can know the morphology, whatever happens to the material. Each one of them does different things. So you can just pick any one of them you want, and then it will tell you the condition. So let's say I decided to pick, even those people working on biology, PCR, there's analysis for PCR somewhere there. And then I can just pick one of this one. It will give you information. So I pick one of them. It gives you this information. So this one, you can upload your data. You can do several analyses as well. You know. So that is it. Do we have any questions?
Any questions?
Okay.
If not,
Okay then.
where is my training certificate?
Huh?
Where is my training certificate?
Okay. So they're going to be, I had the training in Liverpool and Serbia. I spoke with them. If you want a detailed training, this place, because I was awarded a training certificate, I was in Liverpool for a month and Serbia also for a month. But you are not going to go to Liverpool, you are going to be in chemistry department. But I can offer the same training. I spoke with them. But my training covers more than 10 different characterizations. I use the machine myself, and I was trained how to analyze this data by experts. I can offer this training based on the department, and then I have sent them message recently. If any person that takes the training, they can issue a certificate. So if there will be exam. The training is not free. What I mean, when I was doing the training, they will give you all the materials. Now you don't have materials. You're going to have the data. So they have the results. You're going to get the same results. Those are the exams. So if you are able to get the same thing, they give you one material, you can talk everything about the material, and you send the result, they grade you, you get the certificate. I don't know, maybe $100, $200, I don't know. When I went there, I paid almost 4,000 euros. But I've spoken with them. You guys are very rich, you are not going to come there. I will do it here. So I'm waiting for them. If they say that, so they will prepare the exam. You can take it, but then you're going to, not just this, we have a lot of characterization. And I bet with you, I can teach you virtually almost all the characterization. Then you can take the exams. If you pass it, then you can have a certificate from these people. So that guarantees you. Why? We have a student here that graduated. We call him Aye. He currently lives in Canada. When he want to get a job in pharmaceutical industry, I was one of his references. They called me and Dr. Mustafa that this person has given us his CV. And he said he knows how to use GCMSC. He knows how to do this one. You are the supervisor. What can you say before we call him for interview? When I look at what they said to me, I knew that I've taken him to CID. We have used some of this machine together. I told him yes, I'm confident he's able to do that. Now, he works in a pharmaceutical company in Canada. Everything he does in checking the purity, the quality control of this material is characterization he does. When they produce any material, his job, everything, he doesn't do anything. Just characterize this material, pure or non-pure, all these kind of things like that. So, for any person, so we graduate, especially in chemistry materials, if you have a certificate, PhD, and you don't know 10 characterization, I will beg you to keep your certificates. You are not a chemist. Chemists prepare material. Chemist is able to talk. When they have material, they will give you data. You are not going to sleep. You need to do all those things. Tell this. That is what it is. So thank you guys.
Thank you. Let's go. Okay.
Thank you so much.
Thank you for today.
Yeah.
And this is the memory for you
Thank
from
you.
our university.